Okay, so this is perfect. Okay, for those who didn't meet me yet, I'm Felix, first year PhD in Nantes University. So there are a few logos that are completely useless here, but you can see I'm part of the KM3NeT collaboration, and also my lab is Subatech in Nantes. I'm part of this small team of researchers in Nantes. And I try to explain what I'm trying to do with fast radio bursts and high energy neutrinos from KM3NeT. First of all, I'd like to see some hands. Who doesn't know a thing about fast radio burst? Okay, that's good to know. I'll try to be a bit fair in my explanations while trying to stay on time. So first of all, I'll try to have a few explanations on what is KM3NeT. Well, I will take the parallel of Ice Cube, obviously, that you surely know at the time of the week, and a bit about fast radio burst, and finally the analysis strategy we started in my team. So first of all, so KM3NeT is a next generation giant volume neutrino detector that is it is placed in the Mediterranean Sea, so using the Cherenkov as the carrier of the Cherenkov photons. You see there are two sites. One is ORCA, the other is ARCA, and you have here the drawings, like the layout of the two different detectors. So they are in essence exactly the same, but as in Ice Cube you have a deep core and the normal array, let's say. We have here the ARCA detector composed of the two building blocks, just a bit bigger than the Star Destroyer, that is targeting higher energies, right? And for this, we called it Astrophysics Research with Cosmic in the Abyss. And so then we shrunk the strings, right, from 700 meters to 200 meters. We put actually only one building block. And then we have ORCA right there in front, below Marseille. And then we're trying to do Oscillation Research with the Cosmic in the Abyss. So it is the successor of the Nantes experiment that you also might have heard of. Actually, ORCA is exactly at the same site as Nantes, but Nantes has been dismantled finally last year. And the construction started pretty much in 2015. We are now reaching about 20% of the full size. But as you can understand, once we put one string in the water, we can already connect it and take data from it. So actually, with already 20% of the detector, we can make physics out of it. And it is still under construction, but already we are doing physics analysis. So here are a few, well, not very useful numbers, but we have a few strings at the end. That's about 6,000 optical modules and 200,000 PMTs. It will be the largest neutrino detector in the northern hemisphere. Of course, we have another one in the southern hemisphere. Just very briefly about the instrumentation of KM3NeT. So this is a digital optical module. It is a bit different than the ones of Ice Cube. You see, we have it's like a small computer that we put in the water. So it has 31 photomultiplier tubes that are all connected to a central board that will be digitalizing the signal and bringing it back to the shore. Among other things, we have a compass, piezo sensors, many other tools to be able to calibrate, find its real position in the water. And for instance, the 31 photomultiplier tubes are used to increase the area coverage, to have fairly good background discrimination, especially against radioactivity. There is the potassium-40 in the waters that make a high background, but with a very low multiplicity. Basically, the light of the 40K, the potassium-40, will be shining on a few PMTs, and with the multiplicity, we can so multiplicity, the redundancy of the signal detected in several PMTs in the dome, we are able to discriminate it from a signal from a neutrino. And also it enables a hardware failure. Let's say if we lose one PMT out of the 31, it's not that bad. Whereas if we lose the whole dome, it's a bit more problematic. And here down there, you have, for instance, the multiplicity versus the evens for a whole building block. And the area here are the different supernova. signals we are expecting to see in KM3NeT. So basically, the supernova neutrino are at the MeV energy, and when they interact in the waters, it will be shining on only one dome, not on several dome or several strings. So basically, we're able to see an excess of signal for each module, and you can see that already at 6 or 7 PMTs in each module, we are able to detect supernovae of different masses. You have it here, and the background is already below that. So this I will probably skip. We already talked a bit about it. So we have different interactions, charge currents and neutral currents. The graphic here is not really rigorous, but just to say that when the neutrino interacts, it can produce the corresponding lepton with the same flavor, or just with a neutral current another neutrino. And then here it gives enough energy to the quark to make a small hadronic shower, and that is what you see below here, right? So you have those muon tracks that we already talked about. We have all the other interactions that will make basically a hadronic shower. In the case of the tau, if they are energetic enough, they will propagate a bit, and it will make this double bang signature. And of course, the main background is atmospheric muons, but I will not repeat what we said, what was already said by Walter and others. Just to say that the KM3NeT will observe mainly the south hemisphere, where the background from muons is blocked by the Earth, and it's really good, for instance, to observe the galactic plane. But in my case, most of the radio telescopes are located in the northern hemisphere, so we have less FRBs in the south hemisphere. But don't worry, we have a few still. So yeah, just to summarize, we are able to probe from the MeV to the PeV range through all those different subjects of studies. So the supernovae, the nuclear oscillations, a bit of dark matter or exotic matter searches, and the high energy neutrinos for multi-messenger studies. And here you have the map of the effective volume that is planned for at the end of the construction versus the neutrino energy, and you see that the capacity of Antares, so the effective volume is pretty much the effective areas that were shown in the exercises of Walter. And you see it nicely overlaps the capabilities of Antares, but with a bit higher sensitivity. Okay, now for fast radio bursts. I'll try to motivate why it is possible multi-messenger observation. So a fast radio burst is, so we had a large talk on gamma ray bursts, and we can make some sort of parallel with fast radio burst. So it is a very bright and short radio signal that is emitted from extragalactic distances. Basically, this is the energy if we consider the emission to be isotropic. It is less than gamma ray burst, but considering that radio emissions hold much less energy, it is actually huge compared to other radio signals from the galaxy or extragalactic signals. It is of the duration of the millisecond, which makes a very coherent signal over a broad band of energy. I didn't explain, sorry, but this is the spectrogram, and you have here the first FRB ever detected in terms of time and frequency, and you have here the fast radio burst, right, with that saturated all the channels of the Parkes detector in Australia. We have very few information about fast radio bursts. They were first detected in 2007, which is not so long ago. These are the sort of traits that we get from the observation itself, so dispersion measure, rotation measure, some scattering, and we have seen them repeating. The first one was in 2012, also pretty recent. So from these, we can infer some characteristics. I will be not explaining much, but we can come back at the time of questions. But basically, we now determine that most of them are extragalactic sources, and favored emitter is the magnetar, because there was also one multi-wavelength observation with the magnetar SGR 1954 plus 2154, I think, from a galactic magnetar with a hard X-ray burst. And it is a coherent emission, and from all those traits here, we can infer that the environment it is emitted from is an energetic dense magnetized pair to plasma, which is also favoring hadronic and hadronic emissions, and why not neutrinos. From this multi-wavelength coincidence that I mentioned earlier, we have several papers on the possible dual emission of Fermi and neutrino, actually neutrino emissions from magnetar. So the magnetar is the neutron star, a young neutron star with very high magnetic fields. And we have here, for instance, 3 different regions of the magnetar surrounding the magnetar, where we have there is a possible neutrino emission, and down there you have in terms of energy and flux, like redressed flux, the possible neutrino emissions from the different sites. So you can see also here the ice cube sensitivity that is still a bit far from being detected, but we never know until we try, right? Okay, so as to finish, I don't know how much time I have left, not that much, I guess. My strategy is trying at first to be quite simple and quite model independent. As you understand, there is no light curve for Fermis. There is not much we know about those sources, the mechanisms. So we try to be as model independent as possible. What we do is a binned cut and count analysis. So basically, we have a catalog of past radio bursts, and we try to correlate high energy neutrinos to those time and positions of the burst. So we define an on zone around the FRB, an off zone that is larger in the same declination band. From the off zone, we will estimate the background and then rescale it to the on zone. And we also try to optimize cuts on the event, the neutrino event dataset, with something called the model rejection factor that is directly including this Feldman and Cousin's upper limit that we already talked previously. And then, well, yeah, we just look around at the same time and the same position of the FRBs, and we try to have some excess in the compared to background, right? We're trying to compare the signal rate, the real signal rate, to the background rate. And within the background, for the background, we use scrambled data that encapsulates all the detector response and all this sort of things. So we are basically using our detector, the scrambled data, and also within the signal rate. And yeah, just to finish, so for now, the context of the data I used is like for 14 months. And it is a detector that is even smaller, that is actually now in the water. It was using only 6 strings, 6 detection units. So as you can understand, the angular resolution is not as good as we would have with a full building block. And during this time, there were 14 bursts that happened in pretty much the southern hemisphere. This is in equatorial coordinates that were detectable from the ORCA field of view. And the chosen time window is very small, so 1,000 seconds, 17 minutes, centered around the time of the FRB. That ensures us, sort of, that if we detect a neutrino, then it is directly correlated to a multi-messenger observation, sort of. So as I said before, this is done in a blinded way. So I don't have the data yet, the results, but the data will be unblinded soon to obtain the results. And well, in general, we see 0 neutrinos, as you can expect, but we'll see. And then for the future, we are considering a more time-independent method, because this 1,000 second window is very problematic on many point of views. So as was presented before, the unbinned likelihood analysis is very interesting in this case. And I will finish by adding that Ice Cube and Antares have already been searching for FRBs in pretty much sort of the same strategies. So this analysis would be added to those that were previously done. Thank you for your attention.
Questions? one question. Why do you not put ORCA into ARCA?
Oh,
Yeah,
yeah. So yeah, we could basically that makes only one site, but there were several things that were not there at the time why it was chosen. So there is part of political reasons. Probably the main countries that are collaborating are France and Italy, and they were studies for both sides actually. And after, maybe it is possible that that's just a speculation. We have so here lines are separated by 90 meters, and over there separated by about 20 meters on the floor, on the seafloor. And maybe too many lines would be a bit worrisome. Like we use a small submarine robot to navigate through the lines, and there are many things happening down there, all the cables, etc. So it might have been preferable to have just being separated. I don't know, but yeah, we could, but it doesn't change much, right? It's the thing is that for oscillations we need this type of compact detection volume, and putting it within doesn't change much the whole thing.
Can I ask you? Can you make them to the slide which have a different exploration in the magnetar? Yeah. So what is this current sheet region?
Here. Yeah, so the current sheet region is a bit more dense region around the magnetar. So it's basically where you have those magnetic lines that come back, you see, to the magnetar. They change their orientation, and you have some sort of disk of a bit more dense medium, right? Where you have you can find hadrons and more dense electron medium as well. So it is more interesting. Yeah, it is a bit more dense, so you can maybe have a more processes happening over there, acceleration mechanisms and stuff. And I believe it is also linked to this magnetic reconnection, where those lines break and then reconnect, and you have those emissions at this level.
Yes. Where you got the region around the FRB, that you always select the size of this region.
This, right? Yeah. Okay, so this is made with I was very brief on that part, but this is using the model rejection factor. You might have heard of it as the MRF, or also the MDP, the model discovery potential. And this, so basically with this, you have the average Feldman-Cousins upper limit over there, based on the number of background events. And you also put within a signal, an expected signal that is using a very broad spectra, like a very generic spectra. And so then you scan. So the very interesting thing here is that we only have two parameters that we have to optimize. That is, when I explain we have to optimize cuts, there are actually only two parameters that will change the rate between signal and background. This is the BDT score, so the classifier we use to discriminate the signal from background. So we have a classifier that gives the score to each event, right? Which is like 99% signal or 70% signal. And the other one is, sorry, the size, the area, the region of interest, the size. And we scan on this two parameter space, and the MRF is a minimum where we have the best discrimination as possible. So basically we take the minimum of MRF where you have the optimal radius for this region here, and the best BDT score to cut on.
And how does that compare to the angular resolution of the detector?
Yeah, basically we use here the number of background events. So we use data for this, and within the data is encoded also the detector response. So basically, we consider the signal to be from there, and then we have this spreading due to this the angular resolution of the detector itself, and yeah, so we don't have the response itself, but it is appearing as I mean, the worse the detector response, the larger the array size would be. But yeah, as I said, for now we have a very large region of interest sizes, right? You shouldn't show that to an astronomer. Like the radio astronomers, they have like they can pinpoint to the arc second, right? And here we have a few degrees. That is terrifying for them. But okay, with 6 detection units, we can't do much. So the next step would be to increase to like 20%, 50% of the detector itself, and then we'll be able to shrink a bit those regional interest. Yeah, just to finish, to add, like what is said here is that, for instance, for this FRB, even from the FRB itself from the radio telescopes are pinpoint to the arc minute or arc second itself sometimes, but from our detector, even if it's 4 degrees, we can still give it a pretty big significance that it comes from this. It's just that the detector, the neutrino detector, is not accurate enough to have it very close to the FRB real location. So yeah.
Okay.
I think you already answered that.
Okay, good. Sorry, we have to move on. So thank you very much.